Okay, in this video, we're going to go through some solutions for some questions on free radical substitution, esterification, and addition reactions. Okay, so first question, write the overall equation for the reaction between bromine and methane. The first thing to think about when you get a question like this is what type of reaction is it? So try to identify what types of compounds you're dealing with. Methane is an alkane. The only reaction that we learned for alkanes is free radical substitution. Now, obviously in this case, the name is right above us, but on an IB question, that won't be the case. So you'll have to decide which reaction you're dealing with. So we're doing free radical substitution. Substitution means we're going to replace one thing with another thing. So one atom with another atom generally. So if I have methane, all that I can really replace is a hydrogen, and bromine, I've been told, is the other reactant. So the kind of logical conclusion is that you're going to replace a hydrogen, so it goes down to 3, with a bromine, and it's called substitution. That means the hydrogen goes somewhere else, is lost, so it must go with the remaining Br. So even if you don't have all the details memorized, you can kind of work it out just from knowing the name that it's a substitution reaction. The conditions necessary is UV light. That's what causes the bromine to split apart and create free radicals. A free radical is a species with an unpaired electron. And homolytic fission means bond splitting. That's the fission part. And each atom gets 1 electron. So each of the atoms is going to get 1. That's how the radicals are created. The type of reaction that's occurring is substitution, and the mechanism is the free radical part. Okay, actually showing the mechanism. So the initiation, we show the halogen split into 2 radicals. I like to show the dot. Technically, you cannot show the dot, but if you do show the dot, you need to make sure you're consistent throughout showing the dot so that there's a radical present. Okay, a propagation step means you take one of those radicals that you formed. We're going to react it with our alkane. The thing that the halogen is going to bump into is it's going to collide with a hydrogen first, because hydrogen's on the outside. So the first thing that happens is we always rip off a hydrogen from our alkane. So now I've got 3 hydrogens left, and the alkane has now become a radical. Then they want me to show a second propagation. So I take that radical that I formed, and the best thing to do here is to show it react with yet another bromine. So this is a new bromine molecule, another one that's in the reaction container, and that's going to create the halogen or alkane. The CH3 bumps into the bromine molecule, collides with it, breaks that bond. That leaves behind a Br radical. So you're showing these propagation steps, 2 of them to kind of show that they could happen over and over again. And then finally, you show a termination step. A termination step involves 2 radicals colliding and forming a non-radical, which is what ends the reaction. Now, there are other possible termination steps. So for example, 2 of the CH3 radicals could collide. So draw the structural formulas of 2 other possible products. Well, this is another possible product because the 2 CH3 radicals that are in the container could collide and create ethane. So that's another possible product. Another thing that can happen in free radical substitution is that the halogenoalkane that you've made, so this bromomethane, can have other halogens substitute onto it. So you can get CH2Br2, so that would be like if a second bromine added on, and technically you could just keep going, and you could get all the way up to tetrabromomethane. So those are all possible products. I think the most natural 2 that you'd get to are either just the 2 methane radicals coming together or another bromine atom adding on. So those are some free radical substitution questions. We're going to skip now. Let's see. I had some stuff on esters, esterification. So just a practice thing here, trying to name esters. So it can be helpful to draw it out. If you see that COO, then you know, and you see COOC, so you see kook, you know it's your crazy Aunt Esther. And so you've got CO, and then single bonded to O, and now we've got our CH2, CH2, CH3. Okay, now we're trying to name it, and we can say that my crazy aunt Esther got ill from alcohol and the acid that she ate. So we know it's going to end in OH, and we know it's going to have ill. The part here that looks like the carboxylic acid, that's the part that's going to become O8. So this is meth and O8. There's only one carbon in that part. Whereas this part, this long chain that's single bonded to O, that's the part that came from the alcohol. That has 3 carbons, and so that's propyl methanoate. If we're thinking backwards, what created this, that means that what reacted was propanol, propan-1-ol to be more specific, and methanoic acid. Now that wasn't asked here, but just to add a little extra question. Propanol and methanoic acid would have reacted using an H2SO4 catalyst, and this would be an esterification or condensation reaction. We would make the ester above plus water as a byproduct. Okay, and now I'm going to skip ahead to some addition questions. Depending on SL or HL packet, this may be in a different spot. Sorry if this is making you dizzy. Okay, there were a few that we hadn't answered yet, so I'm going to sneak in here and try to answer them now. Okay, what reactants and conditions are needed to produce propan-2-ol in a one-step reaction? So propan-2-ol is CH3, then you've got a carbon in the middle that has an OH on it, and we've got CH3 over here. So we're trying to think about how we can make that reaction. Now, this is sort of what reaction Jackson is all about, what it's for. It has all these different reactions. So try to think about propan-2-ol as an alcohol. So on our chart of reactions, it's sort of over here, and there's 2 different arrows that lead to our alcohols. So we've got one of our addition reactions can get us there. It's called hydration when we add water. And we also have the reaction where we begin as a halogenoalkane and we become an alcohol. So that's called nucleophilic substitution. So really you could pick either. There's 2 different ways to get there. If you had propene, so a 3 carbon, so we're not really changing the carbon chain, right? We're just changing what functional groups they have. So we could do the addition reaction if we began with propene, and if we add water to it in the form of steam, and if we use an H2SO4 catalyst, we could produce propan-2-ol. Now we might also make some propan-1-ol, but mainly we would make propan-2-ol. So that's a possibility. That would be a correct answer to number 5. Another option would be if we started with a halogenoalkane, like 2-bromopropane. So that's a 3 carbon chain with bromine off of the middle carbon, off of the number 2 carbon. And then if we add something like that has hydroxide in it, so something like sodium hydroxide or potassium hydroxide, something that has an OH minus, the OH minus acts as the nucleophile. It replaces or substitutes for the bromine, and you end up with 2-bromopropane. So there's actually 2 different answers, possible answers to this question about the reactants and conditions needed to produce it in one step. Okay, now something that they'll do also is they'll ask you about 2-step reactions. So these are called synthetic route questions. How would you make something in a certain number of steps? And so that's why that reaction Jackson is kind of like this flow chart of what can be turned into what. So bromoethane can be produced by both a 1-step and a 2-step process beginning with ethane. Okay, so ethane is 2 carbons and it's an alkane. So we can follow the alkane general formula to figure out that it's C2H6. Again, thinking about where it is on this flow chart of reactions, remember up top we have alkenes. There's 5 different addition reactions which form the sort of body, and then we've got our alkanes are over here. And there's a couple of substitution reactions. Okay, and now it says that bromoethane can be produced by a 1-step and a 2-step process beginning with ethane. So state the type of reaction that can produce bromoethane in one step and write the chemical equation. So bromoethane would be here. This is where our halogens are, our single halogenoalkanes are. And so to do that in one step, I know that this is a free radical substitution. So I would need to have ethane, I would need to have bromine, and I would need to have the condition of UV light. If that was what, did they ask for that? No, they didn't really ask for that. Sorry, I'm not answering the question. The type of reaction is free radical substitution. And write the chemical equation. So C2H6 plus Br2, and we substitute a hydrogen out, so it goes down to 5, and we make HBr as the other product. Write the balanced equation for both steps of the two-step process to create bromoethane. Name each reaction and state the conditions needed. Now, the two-step one, this is a little bit misleading. I don't think the actual starting material then is ethane. That's kind of a misnomer in the first part of it. The only way I can think to get here in two steps is, well, we can either get there in one step here. We can also get there in one step from our alkanes. If we're going to do two steps, the only thing that you guys would learn, anybody could figure this out, would be to first turn into an alkane of some kind, and then go further, go this way. So I'm thinking that maybe the two-step would be something like you start out with so instead of starting out as an alkane, you actually start out as an alkene. So if you started out as an alkene, and so my apologies, that question isn't very clear. It's going to be maybe impossible for you to answer. But if you start out here, you could first add hydrogen, and that with a nickel catalyst, and that would make ethane. Then you can take that ethane and you can do the reaction that we just talked about with the UV light, and you can end up with our halogenoalkane. So there is a two-step mechanism, but it's worded wrong in the question, so it's kind of hard to answer. Okay, and then finally, question 9, outline a method to distinguish between propane and propene. The classic test is to add bromine, or you can say add bromine water. And what will happen is that the propene will very quickly undergo the bromination reaction, and it will go colorless. As the bromine reacts, the color disappears, whereas the propane will remain brown red because it will undergo free radical substitution if it's exposed to light, but it's a much slower reaction. Okay, so that's going through some practice questions on various topics in organic chemistry.